Hi everyone. Sorry for such a bad Wi-Fi situation and for making you, stay on the call for 15 minutes while I hopped in and out. Again, good job on the presentation today. I think it was very well done. It's a very difficult problem to solve when you have to look for matrices that are the same thing when you cube them. So great work there. Like I said, I'll be recording what I planned on talking about today, but it will be probably shorter because I tend to ask a lot of questions during recitation. But hopefully this will, clear some things up about the content for this week. Um, Before we start though, I like to go over stuff from last week. So last week we talked about inner products, which we saw are represented with, V and W with carets around them. This is essentially just a glorified dot product where whoops, I wrote that down wrong already. You essentially just dot all the entries together like this and you form a scalar. But we see the beauty of this later on where we can start applying this to stuff like functions as well. So this applies to any type of vectors within the vector space. We also have a notion of an orthonormal basis. Here your basis vectors are length 1, and they all are perpendicular to each other, which is super convenient when we're talking about projecting vectors onto a particular basis. And we saw how to form a basis using the Gram-Schmidt procedure. I do want to clear up one formula in the notes that I think could be a little confusing. So let's say we have a basis for R3, and we'll just call it V1, V2, V3. And our goal is to find an orthonormal basis. We denote this E1, E2, E3, and we need to find E1, E2, and E3 using the vectors V1, V2, and V3. So we know kind of how to do this. Our first step to find E1 is we just take V1 and we divide it by its length. So first of all, this gives us the length 1 that we need. And second of all, it's already perpendicular to itself, right? We don't need to worry about making sure it's perpendicular to anything else that we already have. So that's okay. E2 is a little more tricky, but what we do is we denote it W2 over the norm of W2, and we need to find what W2 is, right? We have this formula in the notes. We have W2 is equal to V2 minus the projection onto its S n minus 1, which in our case is just going to be 1. So I'll write that to avoid confusion, of V2. And this is like, a super complicated point in my opinion. So what we can do is we can actually write this out and talk about what it means. For you to be projecting your basis vector V2, this S1 means the subspace. So we're projecting our vector V2 onto a subspace. What's the subspace? Well, the subspace is the span of however many basis vectors we currently have in our orthonormal basis. So when I'm finding W2, I'm really looking at V2. I project it onto E1, divide by E1 squared, right? And then I project that onto the actual vector V1, or E1, sorry. So this right here gives me a scalar, and essentially I'm subtracting off a scaled version of my first orthonormal basis vector from my second one, okay? You don't see this bottom part on here in the formula, right? That's because E1 is length 1, right? So if I square it, I still get 1. We just ignore it in the formula. So that gives us W2, and then essentially what we do there is we normalize it to get E2. And then we do this again to find E3. This is W3 over the norm, over the norm of W3. And again, we have one here where we have W3 is equal to V3 minus the projection onto the second dimensional subspace we have. And I'm projecting V3 onto it. This is literally just V3, and then I'm projecting my vector V3 onto each of my basis vectors I have in my basis, right? But now I have 2 of them. So I subtract off V3 onto E1, and I subtract off of that V3 onto E2. Okay, so I think if you remember this formula instead of this one, you're in good shape. Either way, you follow this procedure and you'll get the right answer here. Okay, so hopefully that cleared up a little bit of Gram-Schmidt. We did a more full-blown example on Thursday last week, but it takes a long time, so we'll skip on to that. Okay, so then this week we talk about inner products again, but this time we have a notion of them with respect to linear transformations. And here essentially we're looking at if I have a v and a w in some vector space, and I have a linear transformation going from v to v, I want to see how this operation, the dot product, right, the inner product, translate through t. Okay, so I'm looking to see how my dot product changes as I move through my linear transformation. We're not really going to look at it in general. In particular, we're going to look at the case when we have the inner product of the vectors that I get when I send through my original vectors is equal to just the inner product of v and w, right? So essentially, I take the inner product of my two vectors, I take their dot product, and that equals the dot product of just the two vectors themselves, okay? This is what we call an orthogonal linear transformation. A lot in the notes about why we call it that. But what we need to care about mostly is that if A is the matrix corresponding to T, if A is orthogonal, then that says that A transpose A is equal to the identity. In particular, A inverse is equal to A transpose. Okay, so that's a super important fact in Math 240, that if you have an orthogonal one, it looks like that. And the most important geometric factor here is that we have A, the matrix, will preserve lengths, THS, angles, and volumes. So you think about it, and there's a lot in the notes about this. These correspond to rotations or reflections in the plane. And yeah, those are super helpful. So you see something like this. I don't quite remember it, but you have sine of theta, cosine of theta, cosine of theta, and minus sine of theta. If I let that be A, essentially what I do is I can multiply this by x and y, and you get some sort of rotation of my vector here. So this is v, and this is A times v. It'll rotate by some angle theta. This is made up on the fly, so maybe it actually goes this way. I'm not quite sure. But that's essentially an idea of an orthogonal linear transformation here. Okay. Cool thing to note is that if you apply the inverse of this, you go the opposite way by theta, and that's kind of interesting as well to get back to your vector v. Yeah, so here's one of the cases where we have an orthogonal linear transformation. The more interesting one that we talk about a lot this week is when we have t of v and w, the inner product of those. This is actually equal to v and t of w, the inner product of those. Okay, so what we see here is that it doesn't matter which of my vectors v or w I apply my linear transformation to, my inner product is conserved. So here we have this fancy word that t is self-adjoint. And essentially what this means in terms of matrices, if A is the transformation matrix for T, A is self-adjoint if and only if A is equal to A transpose. Okay, so this has a whole bunch of consequences that we learned about in the notes, but essentially is correspond to symmetric matrices. And honestly, like, symmetric matrices are cool. We like them a lot, but honestly, who knew that they were going to be this convenient for us to use? Okay, so we have a whole bunch of facts that we can list out for why we like these. Let's start with some interesting ones about the null space and the image. So this one's really cool, in my opinion. So if I have a vector in my null space of A, and I have a vector W in my image of A, if I tell you that A is self-adjoint, then I know that my inner product of V and W will equal 0. Okay, so that's just like, a fact on paper, but let's think about what that actually means. It means that if I take a vector in my null space and a vector in my image, any one of them, I take their inner product, I get 0, that means they're perpendicular. And that means in particular, this is weird to think about, but my null space of A is perpendicular to my image of A, okay? That may not make a whole lot of sense, so let's do an example. Let's say A is equal to 2, 2, 2, 2. Okay, so I know it's not very elegant, but it is a symmetric matrix. So we know A is equal to A transpose. So A is self-adjoint. Let's go ahead and find the null space then. So T, just as a reminder, goes from R2 to R2. My null space of A, I can row reduce it and I get 1, 1, 0, 0. Remember, my null space is everything that gets sent to 0 under A. So my null space is the span of, we can call it just 1 minus 1. How about that? Okay. So convince yourself that that actually is in the null space. Notice that my matrix has rank 1 and nullity 1. So that's the only vector I should be able to find. And then my image of A is the column space of A, right? So that's a throwback. How do we find the column space? Well, we look at our row reduced option here. We select the column with the leading row, or sorry, the leading one, and we go back to our original matrix and select the column that corresponds to that. So we have here that this is a span of the vector 2, 2. We can also reduce that to the vector 1, 1. Okay. And let's plot these, because these are two-dimensional vectors, right? So I can have maybe like x and y here correspond to my columns like that. And so I have my null space here is a span of 1, negative 1. So that is x is equal to minus y. And so in particular, that's a line that looks like this, right? Has slope of negative 1. And as you guessed it, but we can show my image is x is equal to y, right? That's what the span of the column vector 1, 1 means. And so right through here at the origin, I have my image of A. And we know from geometry that these are exactly perpendicular to each other, right? As we decided. So that's cool. That's a cool geometric way of looking at it. The most important thing to come out of this, though, and I think it gets maybe a little glossed over at this point, let's draw a vector here in my R2 space. Let's just call it, let's do here. This is any random vector V. What I can do is I can project V into a part that gets sent to 0, right, onto my null space. And I can also project it onto my image into a part that survives. So I can, for any V, I can find a V in my null space, and I can add that to a V in my image, and it gives me V. Okay, so I can project it essentially into two separate vectors, one that survives and one that dies under my linear transformation. And that's super cool, in my opinion, something I didn't quite know when I took 240 for the first time. but that's a cool fact about self-adjoint matrices. The rest of them are the ones that deal essentially with eigenvalues and eigenvectors. So the next cool fact here is that if A is self-adjoint, then I can't do this, but I can do lambdas are real. These are my eigenvalues. Okay, that's a cool fun fact. I won't prove anything about it, but that's in the notes. And then the next one, A is self-adjoint, means that I have my eigenvectors form an orthonormal basis of the vector space I'm working in. Okay, this is the big one here. That's a terrible box, but that's okay. This is huge because let's think about it. If we know that my eigenvectors form an orthonormal basis, I know that they're linearly independent, right? So if I'm looking at D is equal to P inverse AP, and I know that my eigenvectors span the columns of P, right? That means P is going to be equal to a matrix that has linearly independent vectors in it. That always means that A is going to be diagonalizable. So that's a requirement, right? I need to be able to fill up P with linearly independent eigenvectors, and that's exactly what I do. That's great. That's really, really good. So if we have a symmetric matrix, we always know it's going to be diagonalizable. And then, in fact, what we can do is we can form an orthonormal basis out of them, okay? So because of that, what we can do is we can form, sorry, let me think. Where does this come from? We also have this notion that P inverse is equal to P transpose. That's in the notes as well. So when we're looking at D is equal to P inverse AP, what we're actually looking at is P transpose AP. And this is also pretty important because you don't have to find an inverse anymore. That's a pain in the butt to do, right? If you have a 3x3 matrix. I'm used to using Symbolab to doing stuff like that, but now it's pretty easy because I can just, flip it on its side and make it into its transpose and do this multiplication instead. So it's pretty simple to do that. And in fact, this has a ton of applications. Like when I took Physics 411, which is Intro to Quantum, we essentially assumed that all of our matrices that correspond to quantum operators are self-adjoint. So I didn't take a single matrix inverse like the entire semester, which was, I'm very thankful for that because it's not super fun to do. Okay, but anyway, if this is true, right here, then we can find all of our eigenvectors and we can construct an orthonormal basis with them. So let's do an example then. Let's do find an orthonormal set of eigenvectors of this matrix here. The first thing we notice is it's symmetric, right? So A is self-adjoint. Which means that I can find orthonormal basis of eigenvectors, which is good because that's what the question says, right? Okay, so what do? Well, we find the eigenvalues, we find the eigenvectors, and then we make them into an orthonormal basis, okay? So we do our normal way. We do the determinant of A minus lambda I. We know how to do that. We set it equal to 0. In this particular case, we get negative lambda minus 1 squared times lambda minus 7. All right, we don't really care about the minus sign, right? That doesn't do anything for us. So that tells us that I have lambda 1 is equal to 1. Sorry, let's do it the other way. Let's do lambda 1 is equal to 7 with multiplicity 1. And I have lambda 2 is equal to 1 with multiplicity 2. Okay, so remember from last week, we get in a little bit, we get a little worried when we see this multiplicity 2. We'd be wondering if it's possible to diagonalize this matrix A. But what we know from above is it's always able to be diagonalizable if it's self-adjoint. So what that tells us then is if I have a multiplicity 2 of some eigenvalue, I should be able to find 2 linearly independent eigenvectors. Which is wonderful, because I don't have to do any of that Jordan form that we learned last week. Okay, so let's go ahead and find them then. We can start with lambda 1 is equal to 7. So I have a minus 7i is equal to minus 5, 2, 1, 2, minus 2, 2, 1, 2, minus 5. And not a bad guess is 1, 2, 1. Cool. I don't know why I called it W. Give me one sec. Yeah, I don't really need to call it W, but I did in my notes, so let's keep it that way. Okay, so here's one eigenvector. And what we're going to do here is we're going to use that to construct our orthonormal basis, okay? So, you know what, honestly, let's just call this V and see what happens. That's what it should be. V1 is one of our eigenvectors, and we need to look for E1. Well, we know how to find E1, right? It's just V1 over the norm of V1. You can convince yourself that the norm of V1 is the square root of 6. So I have 1 squared plus 2 squared plus 1 squared over the square root. This is 1 over root 6 times V1. So that gives me 1 over root 6, 2 over root 6, and 1 over root 6. Okay, so here's my first orthonormal basis vector. Let's do lambda 2. Lambda 2 is equal to 1. I have A minus just the identity matrix here is equal to 1, 2, 1, 2, 4, 2, 1, 2, 1. That's nice for us, right? If we row reduce this one time, we get 1, 2, 1, and 2 rows of zeros. That's perfect, right? So I have rank 1, nullity 2, which is perfect because that's exactly what I needed to find 2 linearly independent eigenvectors. Let's go ahead and find them. So we can call V2, one of them that works is 2, minus 1, 0. And let's go ahead and find V3 as well, which could be 0, 1, minus 2. So these are my 2 linearly independent eigenvectors that I found. And then I need to find an orthonormal basis for this one. So E2 is equal to V2 minus, oh, I see why I call them W now, okay. So E2 is equal to W2 over the norm of W2, right? So I'm just renaming them. If we go up here to this formula that we talked about earlier, I have this right here, that W2 itself is equal to V2 minus the projection of V2 onto my first dimensional subspace. We know that to be just the projection onto the basis eigenvector I have. So W2 is equal to V2 minus V2 E1 onto E1. Okay, so we can go ahead and figure out what that is. It's a lot of messy algebra, but essentially we get that sorry, we actually don't have to do this. I'm losing my mind a bit. I apologize. So we already know that eigenvectors corresponding to different eigenvalues are going to be linearly independent. So we actually start the Gram-Schmidt procedure from here. Okay, so it's literally, we start this over and we say E2 is equal to V2 over the norm of V2. So we're starting a Gram-Schmidt procedure over for our second eigenvalue here. And so what we get here is just the norm of V2, we can convince ourselves, is 1 over root 5. So I get 1 over root 5 times V2, which is equal to 2 over root 5 minus 1 over root 5 and 0. Okay, so sorry that wasn't super clear, but what we're doing is we're considering this to be on its own a normalized eigenvector, and we're considering this to be on its own as well, 1, but now we have to use E2 to generate E3 because they're within the same eigenvalue up here. Okay, so now we say that E3, which we generate using V3 and E2, is equal to W2 over the norm, W3 over the norm of W3, where we know that W3 is equal to V3 minus the projection onto E2. Okay, so we can go ahead and figure out what that is. We have V3 E2 is equal to just the dot product of V3 with E2. So I have 0, 1, minus 2, dotted with 2 over root 5, minus 1 over root 5, and 0. Notice that the only term that survives here is this 1 and this minus 1 over root 5. So I get minus 1 over root 5. And I'm using that to scale E2. So I get that W3 is equal to V3, 0, 1, minus 2, minus negative 1 over root 5 gives me plus 1 over root 5 times V2, which is 2 over root 5, minus 1 over root 5, and 0. So that means that W3 is equal to 2/5 minus, oh, sorry, this is a 1. Yeah, 1 minus 1/5 is minus 4/5. And then this minus 2 remains the same because of the 0 back here. Okay, so the math checks out here. And that's W3. The last thing we need to do is normalize it. So E3 is equal to W3 over the norm of W3. The norm of W3, not super fun, but it's the square root of 14 over 5. So I have root 5 over 14 times W3, which is equal to, yeah, again, not super fun, but it's 2 root 5 over 5 root 14 minus 4 root 5 over 5 root 14 and minus 2 root 5 over root 14. And we'll make that more clear that that's a vector by doing this. Okay, and that's our third orthonormal basis vector. Okay, so we have a set. What we should do is make sure that they're actually perpendicular, right? So we know they're all length 1 because we did this step in each of them, but we're not exactly sure if they're perpendicular. I'm at least not convinced, right? So let's check that E1 perpendicular to E2. How do we do that? Well, we take the inner product or the dot product of them. And I notice that when I dot E1 with E2, we can do it out. This is 1 over root 6, 2 over root 6, and 1 over root 6. I'm dotting that with 2 over root 5 minus 1 over root 5 and 0. And that works out perfectly, right? Because this right here, it doesn't really matter about the root 6s and root 5s, right? But I have 1 times something, 1 of something times 2 of something else, and then I have 2 of something minus 1 times that something else. That easily gives me 0. I can see that pretty well. I need to check that E2 perpendicular to E3. So I take E2 dotted with E3, and I see what I get. But if I do that, I get 2 root 5 minus 1 over root 5 and 0. And then I get 2 of something minus 4 of that same something, right? And something else that I don't really care about, right? So I have this 0 here. It makes me not care about this last thing. And then I have 2 times something times 2 times something else. And then I have minus 1 times something. Here, I messed up somewhere. That's not a minus, is it? No, it is. Sorry, I got my minuses messed up somewhere. This should not be a minus 4. I'm sorry, yeah. This right here, this is a plus 1, and this is a minus 1/5, so this should be positive. I'm really sorry about that. It should be positive here. The norm stays the same, the negative doesn't matter, but all I have to do is erase right here and we're good to go. So this should be a positive 4 here. Hopefully that didn't confuse everyone 5 minutes ago, but I'm sure it did. Again, that something else doesn't matter because of the 0, and then I have 4 over root 5 minus 4 over root 5 gives me 0 as well. So that's good. Last thing I have to check is that E1 is perpendicular to E3. And so here what I do, E1 dot E3 is equal to 1 over root 6, 2 over root 6, and 1 over root 6. I'm dotting that with, I'm going to take everything with me this time. 2 root 5 over 5 root 14, 4 root 5 over 5 root 14, and minus 2 root 5 over root 14. I'm going to ignore the root 5s and the root 6s, but I have essentially I have 2/5 from this one here. If I ignore all the factors of the square roots, I have plus 8/5 using these two. And then I have a missing factor of a 5th right here. So I just have minus 10/5 from that last term here, which does indeed give me 0 as expected. Okay, so I know that was a long walk to get here, but we do indeed have an orthonormal basis where it's E1, E2, and E3, as we just found above. And the beauty for why we were able to do that is because we started with a matrix that was symmetric and therefore self-adjoint. Okay, so that's all I had planned for today. I had hoped that there would be questions about stuff coming up on the requiz, but I'll be happy to answer them via email if you got this far during this recitation. Yeah, good luck on the quiz on Friday, and please let me know if you have any questions.